Hello, everybody. My name is Mark Chupka. I'm the Vice President for Research and Programs here at the Energy Storage Association. Thank you for attending today's webinar titled Assuming Control, the Software Revolution in Energy Storage. This webinar is being recorded. Everyone who registered will also receive a link to the recording and slides within the next couple of days. Questions can be submitted at any time via the questions chat box in your browser, and we'll get to those after our speakers finish their presentations. In the text of your question, please indicate to whom you would like your question addressed. All meetings and teleconferences of the Energy Storage Association are held in accordance with our Antitrust Guidelines. We ask that you abide by these guidelines during today's webinar. The full guidelines are available in the member area of the ESA website. If you are not yet an ESA member and would like more information, you can reach out to my colleague, Brenda Lovell. Membership includes free access to all of our webinars, including many that are exclusively for members, among other numerous benefits. Please contact Brenda for more information. Among our benefits is a wide array of informative products. ESA now offers our members a way to choose what communications you would want to receive from ESA. You can select among policy, events, and member news to customize your member experience. Before we begin, I'd like to tell you about an upcoming event. Registration is now open for the ESA Annual Conference, which will be held in Phoenix on December 1st through 3rd. Please visit our website for more details, and it will be great to see everyone again. Today, we are exploring the crucial role that software is playing in improving the efficiency, safety, and profitability of operating battery energy storage systems. From the outside, batteries are deceptively simple insofar as they really only do three things: charge, discharge, and wait. It is software that transforms an otherwise simple machine into a complex, flexible, and valuable asset that enables the clean and reliable grid of the future. I'm delighted to introduce a great panel for today's discussion. First up will be Alan Cordova, Senior Director of Business Development at Fluence. Alan will give an overview of the many tasks that software performs in battery energy storage systems, including how artificial intelligence software can optimize the battery economic performance. Daniel Kratzer will be next. He is the CEO of Fractal EMS. Dan will focus on the asset-level software that keeps the battery energy storage system operating safely and efficiently over its lifetime. Our final presenter is Joshua Lehman, Senior Director of Product Management at STEM. Josh will take a deeper dive into market participation software and how artificial intelligence can enhance economic performance in organized markets, even linking together distributed resources to optimize overall market value. After their remarks, we'll open up to audience Q&A. You can ask questions via the question chat box at any time, and we'll read those out for the presenters when we get back to the Q&A session at the end. Now I'll turn it over to Alan.
Good morning, folks. Good afternoon, folks on the East Coast. Thank you, Mark, for hosting the webinar today. I'm going to talk briefly about the AI revolution in energy storage as it pertains to wholesale market participation. So, got 5 quick items on our agenda today. First, quick overview of Fluence. Second, how software interacts with storage at a very high level. Third, how energy markets work and how storage can participate. Fourth, how we measure how well storage is participating in the market, and then finally, why the AI really shines in energy storage, and why storage is a great use case for the automated bid management. So let's dive in here. There we go. So Fluence is a leader in energy storage, and in particular, just want to highlight the work that my team does. Fluence overall provides storage systems globally. My team in particular focuses on the optimization of energy assets. We look at the application of those assets in wholesale markets. You may have known my team is the former AMS. Was acquired by Fluence in October 2020. We have met a lot of success in Australia, which is one of the most challenging markets to operate. It's an excellent case for AI, where we are managing bids for over 2.7 gigawatts of assets, and we're expanding quickly in the United States. Advancing. All right, so just kind of lay out a few key concepts here, kind of terms you may have heard of. Storage is software is present throughout storage. It's much, and so it's kind of useful to think about different. I like to think about different layers of software. The very basic level, you have kind of the battery management system, the BESS you may have heard of, making sure that the cells are performing, that they are, kind of within tolerance. You have the power conditioning system that inverts the power between direct current and alternating current. And then you have the energy management system that's sort of making sure the entire system is functioning, and is receiving relays from the grid, and is also broadcasting key indicators for performance. Next slide here. All that is sort of, within, inside the fence, so to speak, on a project site. For us, we think about that as kind of the asset level controls. And then we zoom out to look at the broader picture of how that asset interacts with the broader marketplace. So the market operator in this case, if you're in California, it's CAISO. If you're in Texas, it's ERCOT. They are, running hourly, daily markets in which energy assets, be they coal or gas-fired power plants or storage, can participate. And then you have economic owners, so either the plant owner themselves or someone who's bought the right to operate the plant. If you think about a toll, that could be someone else. And then they can see the asset, like a stock trader with a book of business, where they have this right to use the asset as they see fit, and are looking to enter that asset in the market in the most profitable way. And so the question then becomes, well, what is that? What is that way? How do they do that? And so what software does in general at this level is, first, facilitate the communication between the economic rights owner, the asset, and the market operator. And then second, on top of that, help the economic rights owner determine the correct way to participate in the market so that this rights owner can maximize profit. So just in terms of what is the market itself, I think about it at a very basic level as a set of products. Energy is pretty straightforward. Charge, discharge, you buy and sell. But there are also what are known as ancillary services, which I kind of like to think of as like options. You're giving the grid operator the right, but not the obligation to discharge the asset, in particular to meet needs on the grid. If there's a generation shortfall or voltage issue, the grid operator needs very quickly to remedy that to serve reliability needs. And so ancillary services are a way to do that, in a competitive marketplace. And storage in particular, for regulation, which is a fast responding ancillary service, can perform and compete quite well in that particular product category. So how do storage assets bid into the market? One key concept here is the idea of bid curves. So instead of just bidding price and quantity, like, okay, I'm going to sell 20 megawatts for $20 a megawatt hour, many products and many markets allow for a curve where you can, offer to buy a certain amount. So in this case, it's sort of negative megawatts for a certain price. And then at the same time, you can offer to sell for a certain price. And, that concept of a bid curve can be used to indicate, where you want the assets to go. If you can say, look, if you the grid operator, or you the off-taker, or the counterparty, really want to, buy energy from me, if you want me to sell energy, I can do that, but it's going to cost you. But I'd much rather buy energy at this point, so I'm going to make, bring the cost at which I'm willing to buy energy closer to the market price. and therefore increase my chance of getting awarded for a buy signal versus a sell signal. But this bid curve gives us a lot more flexibility, in every hour in terms of how we can manage our assets. On the right-hand side is more the telemetry side of things. The economic rights owner, somebody who's going to be bidding the asset, they work through an entity known as a scheduling coordinator, which is the interface to the market. The scheduling coordinator, receives the bids, makes sure that the bids are compliant, submits them to the market, and then receives the awards and settlements from the market itself. Another dimension to this, besides the product, is the time element. So, many markets have, are run twice. So the first run is the day-ahead market. So, we just passed 10 a.m. here on the West Coast, so the California market closed for tomorrow. So, 12 minutes ago, CAISO settled, how much energy, how much ancillary service will be bought and sold at every price node, for every hour of, tomorrow, Friday. That is done, this kind of one pass, and really is the primary vehicle by which the grid operator utilities procure energy. However, there's always, needs, on the margins, maybe load forecast was off, or, it was a cloudy day that was not forecast. And so CAISO and other market operators also run a real-time market, every 75 minutes before the hour, that can help kind of fill in the gaps. And for many market operators, the idea is that there's a cascaded market design, and so you want to solve you're ideally trying to solve tomorrow's energy needs in the day-ahead market, and not go to a real-time market. CAISO is very kind of structured in that way. Other markets, are more flexible, where like the Australia market, for example, is much more focused on the real time, and so each the interaction between these two markets and the idea of the design of the market plays an important role in how we think about how our software can serve these energy storage products. So we've got a range of products, we've got a range of we've got these two markets. We also have this notion of a bid curve that can really give us that kind of flexibility. And so when we think about what are the bids that are being delivered, think about kind of three underlying services that need to be performed. One is price forecasting. So not just sort of what exactly is the price, but what are the possible range of prices. The second is asset optimization. So do we chase an opportunity today, while maybe pushing the technical constraints of the asset, or do we think about the constraints, and then finally is kind of deciding on the bid, and in that real-time market you've got to bid every hour, and so there's a lot of sort of technical requirement that you make very rapid decisions around the structure of your bid. So for us, we look at when we kind of put this together, we think about performance of our system and performance of a automated bid management system, and we typically look at uplift. So we can simulate how a manual human trader might bid in the marketplace, and then we look at how our system would work. And for a lot of manual traders, for human traders, they may look at a specific strategy and just continue applying that strategy throughout the year. So a lot of folks will talk about, well, I'm just going to do energy arbitrage, buy the 4 lowest hours, sell the 4 highest hours. And yeah, you can make a certain amount of money, and in this case, like you'll make a decent amount of money in the day-ahead energy market, which is kind of the most common form. But an automated trader will look at that against other opportunities, particularly in ancillary services, and consider maybe there are better opportunities elsewhere. AI has the ability to look, as you said, across a wide range of constraints. I think about sort of a finite but large data set to consider, something that no human trader could think about. And particularly in this market with these complexities, automated bid management can be, highly effective and make better decisions than even the smartest, most experienced trader. And the other thing also is that, automated bid management uses machine learning to constantly train and improve models. So as conditions evolve, as the grids change, this machine learning will constantly be, retraining for new situations and helping the AI, continue its, price forecasting and asset optimization excellence. So just finally, we, this is all nice to talk about. We've actually seen considerable benefit here through this process, and we've had a lot of success in Australia. Beating what human traders could otherwise do. We've been selected in the U.S. by major utilities to manage their bids for their large assets, and we're really excited about this application, this use case, not just as kind of an elegant way to deploy AI and machine learning, but also as a way to get more bang for your buck, so to speak, for your energy storage assets, and ultimately big picture to advance the decarbonization of the grid. So with that, I'll turn it over to Daniel from Fractal EMS.
Excellent. Thank you so much, Alan. And thank you for everyone for joining. I'd like to go through the internals of a system and essentially piece together what Alan and Josh are going to are presenting on, and that's how does this all work? Alan talked a lot about bid optimization. How do you do that at site, and how you do that with the controls? And the important thing to know about storage is it's crucial that you have good software. And if I could give you an analogy, if gas turbines, if wind, solar, kind of like flying an airplane where you have a pilot and you have people flying the airplane, and you have a lot of on the ground boots on the ground that help manage a site. Well, storage is unmanned, and so it's like flying a drone. And with drones, you need really good software, you need really good situational awareness, you need low latency, and you need to be able to diagnose things remotely. So that's the difference between traditional assets and storage. You need really great software. And by and large, we can kind of separate the different functions that you need into these four categories. So on-site controls, what you have in the cloud, your O&M, and then a lot of what Alan ended up talking about, the bid optimization. All right, and I'm going to focus a lot on three of them. I'm not going to focus so much on O&M today. So I'm going to show you how, other than O&M, how these work. And for those of you who are interested, this is a diagram of how a site could look as far as kind of overall architecture. And with storage, you generally have these lower level devices or edge devices that communicate directly with the inverter, HVAC, the BMS, fire suppression, and then those are aggregated at the site level, and you have a site controller which manages the power distribution. That site controller could be speaking with outside entities, a utility, an ISO, a third-party API that's feeding it power commands, much like STEM does. And then you eventually get to your cloud, and you'll see a lot of what we have in the cloud, the things like reporting and where you keep all your data, and analytics that helps you, that feeds what Fluence is doing. There we go. So the landscape is that there are quite a few people who have done storage, and but what often gets confused is that EMS, the word EMS, is used quite a bit. And it's kind of like when people say, I work in IT. Well, what does that mean? Do you work in networking? Do you manage software? Do you help build servers? So in a similar fashion, when someone says EMS, it's a good idea to ask, well, okay, well, what's your scope? And the first group on the left, these are names you're probably familiar with. So these are integrators that can offer you a turnkey system. And they can come in with a proper amount of software. Many of them also are able to install the hardware, or at least cause the hardware to be installed. And so you have this nice platform. Then you have the middle column, which is a little bit newer. These are people who um, will offer their software separately from a full integration service, from a full turnkey contract. And these maybe whether you call them third party or independent, these are people who will allow you to use their software, and then you can choose what hardware you want to buy, which EPC you want to go with, etc. And then you have the people on the right, and I'm sorry, I would say to a large degree, someone like Fluence also is in the right. So they're a little more vertical, but STEM, very much someone who will optimize how you use your storage asset, and Josh will be talking about that today. And the way it typically works is the people in the right-hand table will send either schedules or power commands to the EMS that's on site. And so the two work together. A lot of things differentiate EMS, and I'm going to go through some of them today in a demo. I'm not going to go through this list, but lots of different options, lots of different capabilities, lots of different granularity to what an EMS can provide from one vendor to the next. But I would say if we are trying to drill down, if I could convince you, what are the important parts of an EMS? It's these 8 things. And I will actually be going through a demo with you here. And I'm going to show you some of these 8 things. So the first one being the real-time visualization. This is the ability to go into a dashboard and just see what's happening at your site. And there are important things that you should instantly be aware of. And so that's the site power level, SOC, temperatures, and then there are other things like on this page that's on the right. Maybe you have some PV, maybe you have some wind, and you're interested in the weather. So it's really important to be able to have situational awareness and for you to be able to get that quickly. As we dive deeper, another really important aspect to an EMS is the ability to operate this plant remotely. And whether you're doing that at the site level with site level commands, or if you're doing it at a string or unit level, where you can operate the battery contactors, PCS, etc. So you can go in and be able to individually change things. And being able to come in, take a look at what's happening with your battery voltages, your temperatures, combined with the ability to remotely operate, it helps you be able to efficiently and remotely operate the site. The next thing, and this means this could mean a whole lot of things, but being able to access your EMS via different platforms. So whether there's another website, this could be STEM sending you commands. This could be SCADA coming in from KISO or from ERCOT. Could be things coming in from on-site, but the ability to intake things and be able to take action on them, very important. Next thing is the ability to investigate anything that's happened. So any notifications that you've gotten. So this could be warnings, false alarms. So being able to go in and do root cause analysis and perhaps things like filters and searches, that helps you to do that. Related to that, if say you have an operator that fat fingers something, well, it's really important to be able to come in and take a look to see when and what happened, and you know who might have done it. So you want to keep logs of everything. And then when you're curious about operations, so let me go back here. Well, when you're curious about operations, you can go into a site, and you should be able to bring up data. And whether you want to just kind of download data or whether you want to visualize it, you know, you need to be able to come in and just take a look at what's happened in either the recent past or, you know, far-flung past. But being able to access your data, being able to graph it, export it via CSV, maybe just taking a picture of it. You want to be able to do that, and it needs to be seamless with your platform. Along with that, you want to be able to have reporting that's embedded with your EMS, right? And this reporting, if you know, optimally, will be something that you can also modify, that you can you know, make it custom to yourself. So you know, be able to go in and just taking a look at your performance, taking a look at health, taking a look at run times of certain equipment. I would say a big one being, you know, how have your KPIs been performing? You know, maybe you have an off-taker that's using your battery, so you want to make sure that the off-taker is adhering to the contract. Vice versa, you want to make sure that as an owner, you're adhering to your supply contract with the vendor, and you're staying below any performance guarantees. One of the big ones that is going to become more and more popular as storage continues to grow is the ability to do analytics, both on the revenue side, like STEM influence, but also on the health side. And at Fractal, you can come in and we will go through the battery data, and we will let you know which batteries are anomalous or anomalies, and which battery modules we should keep track of, either for fire safety reasons or because they're weak. And so this is an automated process that, after years of doing this, will really help the health and longevity of your system, because a bad module and a bad set of racks, which becomes a bad set of racks, can pretty much act like a cancer and cause your system to die before you want it to. One last thing, just you know, there are you know, both Fluence and AMS are talking about this. You know, they're describing how you do the bid optimization. Well, I'll just show you real quick what that might look like in practice. So after someone like Fluence, you know, goes in and optimizes what they're going to do with a battery asset, well, you can come in to something like the Fractal model, and the way it interacts is well, after a little bit of confirmations, you will be able to take the prices that have come in on your asset and then optimize how you dispatch that asset. So in this case, if let's see, if I show you a site, let me bring it down for you. So this is the current schedule, and this schedule, we don't have anything for tomorrow, right? But we know we want to optimize how we're going to use this asset. So you know, it could be as simple as selecting a certain amount of hours tomorrow, and then sending this schedule to your battery, right? And with a lot of cybersecurity aspects to it. But what we're doing here is the different colors represent the different services that Alan had talked about. And now we're sending this to our battery. One more confirmation. And if we go back to our battery, and refresh this page, we now see that we have some activities on Friday, right? And so, this could be done somewhat manually, like I just showed you, or someone like Fluence or AMS could just send it directly to the on-site controls. So I'll just finish up with a couple slides here. And I'm going to hand off control. There we go. And the last couple of thoughts, and with fire being at the top of a lot of people's minds, the EMS should be heavily involved in the fire system. And the thing to know about fire system, really two components to it. It's detection using different types of fire detection, and then it's suppression. And both these topics we could probably spend hours on. But the EMS should be keyed in on both. And so anytime there's a protective action at site that the fire system takes, we also recommend that the EMS sends out, whether you want to call it an electronic e-stop or a fast stop, but it should be involved in that aspect, and it should also inform anyone that's that should be informed on top of the fire system informing that something has happened. And then the last one, and this is going to be important for the rest of our lives, it's cyber. And with cyber, it's kind of like that story about being chased by a bear. The two guys being chased by a bear. One guy takes his time and puts on shoes. Another guy's like, well, what are you doing? The bear's chasing us. He's gonna eat us. He's like, well, he's not gonna eat us if I can run faster than you. So that's the same thing with cyber. You just don't want to be the low-hanging fruit. You want to do your best to stay ahead of it. And 5 years from now, we'll laugh about kind of our techniques that we have today. But we just have to keep trying, and we have to avoid being easy to hack. All right. Well, I really appreciate everyone on the line, and looking forward to questions. And I will hand it over to Josh at STEM.
Great. Thanks, Daniel. And thanks, Mark and ESA for having me on this webinar. I'm going to start by touching on something I think we all know, which is that as renewables adoption continues to accelerate, storage is needed to stabilize the grid and to make further adoption of renewables successful. So STEM's business model involves us deploying our AI software, which we call Athena, to manage energy storage systems and to optimize them over time. Athena ingests data inputs from a variety of sources to generate forecasts of energy prices, solar generations, and other site conditions, and then we use those forecasts to optimize the bidding and operations of assets in wholesale markets. So many of you may be familiar with this image. It's the Rocky Mountain Institute, which has recently rebranded themselves as RMI. So their wheel of services that energy storage can provide. When RMI released its value of energy storage report with this graphic in 2015, at STEM, we saw this as a roadmap for ourselves in many ways. Since then, we've expanded the Athena platform to where it is now, which is delivering 11 out of the 13 value streams which were identified in this wheel. That includes value sold in wholesale markets, value sold through direct bilateral contracts with utilities and distribution operators, as well as services delivered to end consumers of power at the commercial and industrial scale. In 2016, STEM began operating energy storage systems to provide resource adequacy in California. And our fleet of storage systems has grown 50x since then, including both front of the meter and standalone storage and solar. Front of the meter, standalone storage and solar, as well as behind the meter aggregations or virtual power plants that comprise hundreds of energy storage systems which participate as an aggregated resource. And what you see on the graphic here is an example of one day this past summer where STEM had a number of calls for resource adequacy in California, and we were dispatching aggregations of behind the meter commercial industrial connected energy storage assets into or to fulfill a resource adequacy obligation. So energy storage is growing for many different reasons and in many different markets. In particular, what we are seeing is a very high adoption rate of solar and storage as hybrid resources that are interconnecting together in the market. This allows the asset owner to shift when the solar production is sold into the market. It allows the site to provide more consistent availability for capacity, and also can make more value out of the solar generation by abiding by interconnection constraints in the case of DC coupled systems. And these solar and storage applications also bring us to the first application that we typically get asked for about machine learning when it comes to power plant operations, and that is solar charging. By charging the battery from solar generation, asset owners are able to count the storage system cost in the eligible cost basis for the solar investment tax credit. Solar charging, however, requires a good forecast of solar production, and AI-enabled software will feed a machine learning model with historical solar production, solar asset information, weather data, and other inputs. And that model will then produce a forecast of solar production, which tells us when the storage system can be charged. So that information can then be fed into an optimization problem. And this slide gives us more full cycle view of economic optimization for market participation. So it begins with those forecasts, such as the one we just discussed. And there's additional forecasts that we need, and the most clear ones being market price forecasts for energy, regulation prices that will inform our bidding strategy later on. On top of that, we also will build in constraints, such as constraints at the point of interconnection, the warranty limitations of the battery, in terms of number of cycles or resting state of charge, and other factors. And all of that, those forecasting constraints are fed into this optimization, which determines how best to monetize the storage assets. The result of that optimization is turned into a set of bids in the form of price quantity pairs, which are then submitted into the ISO. So this is a little more detailed, granular view of what that looks like over a week of operations. So the dotted lines here on this graph represent the high and low limits that Athena has bid for frequency regulation for this asset. The blue line is the AGC, the automated generator command that we actually get to be dispatched from the ISO. So we see a few things. First, the high and low limits vary day to day, and the reason for that is that because ISO New England treats frequency regulation as a single product, frequency reg up and reg down are not separate products. Anytime we bid into frequency regulation, we need to make sure we do that during a time when there is sufficient solar production to allow us to charge the battery. So that's one limit. The other limit is the point of interconnection constraint, where the combined output of the storage and the solar can't exceed a certain value based on the interconnection limitations. So this is a distribution connected asset, so we're limited to 5 megawatts at the point of interconnection. To add complexity on top of that, this is a 2R site. So that means that the storage and solar are separate resources. And the solar is a generator, a settlement only generator. So it will always get paid the real-time price, whereas storage here is a continuous storage facility, or CSF. And as a CSF, the storage actually has to buy power from the grid, even if it's charging at the same time the solar is discharging. So these bids are made with the context and the information of what the solar is doing, but also meant to independently maximize value of storage. So we talked about frequency regulation, and you see generally the power commands, the generator commands will stay within the dotted lines here that we set for frequency regulation. But you also see some excursions outside of that. So on the far left, there's one day where the generator command goes below the frequency regulation limit, and that's because we are participating in the energy markets as well as frequency regulation. So the system is not only providing frequency, but also it's making a transaction in the real-time energy markets. There's also other times when you'll see, say in the middle or some of the days over towards the right, where there's no bid in frequency regulation, so the dotted lines are at 0, and the generator command still goes up and down. And that's because at those times we are transacting in the energy markets. And there's a few reasons we would do that. One is to arbitrage energy prices. Another is to charge up get the system up to a high state of charge to give ourselves the opportunity to participate in or to take advantage of a real-time price spike. And finally, this system, a particular system, is in Massachusetts, where there's opportunities to get credits for discharge at certain times of the day. So Clean Peaks credits and MA Smart revenues, for those familiar with those programs, rely on when the system is discharged. So we will discharge the system by having a bid clear in the energy markets, which will cause us to discharge, and then we not only get the revenue from the wholesale market at that time, we also will get the credits earned through those programs. So the entire loop of forecasting, optimization, and bidding is automated based on the objectives and the risk tolerance of the asset owner. The bid strategy can be adjusted at any time. And as Alan mentioned earlier, the frequency with which this loop happens and in which these bids are submitted to the market vary by the market and also the market product. But just as an illustration I've put together, so the real-time controls are dictated by the automated generator command, which is typically a 4-second signal, and at times by autonomous site response to frequency. So it's either in the case of the day-ahead market, it would be once a day. In the case of the real-time market, in some place like ICE in New England, it would be once every hour because the market clears every hour. In a 5-minute market, then we would run this forecast, optimize, and scheduling and bid loop every 5 minutes. Beyond that, the machine learning models need to be continuously updated to remain accurate. So every so often, we need to tune those models. In this example, I've put it as monthly, but it really varies according to the system and the application. And finally, over time, the AI system can always be improved. And at STEM, we've got a team of 60 software engineers, and I will make a shameless plug that we are growing our product management and software teams for anybody interested in that kind of work. And that team is continuously expanding the capabilities of Athena and building in new features, finding more data that can further improve our forecasts and increasing the capabilities of our optimization to work in new markets and abide by the market rules of new wholesale markets as we move along. So I'd like to close by saying that energy storage has come a very long way, but we are still just at the beginning of its trajectory. I have some numbers here from Wood Mackenzie and Bloomberg, which forecast extremely bullish growth for the growth of storage throughout this decade, and we are incredibly excited by what the future holds. So with that, I will hand it over to Mark for Q&A.
Thanks so much to all the presenters. That was an incredibly informative session. Many of you have already submitted questions, and you can continue to ask questions during the Q&A session as well by using the questions chat box in your browser. We have a lot of questions. I'm going to start with one that was submitted during Alan's presentation, but I think Alan, Josh certainly would probably want to address this. The question is, what is the standard on adding and managing a wide range of asset types and availability in real time with multiple market operators? So Alan, you might want to take a crack at that, and then Josh.
Yeah, maybe I'm not sure what standard means. Is it about like a standard for telemetry?
I wasn't sure either.
Or standard or custom?
It may be a normative statement. You know, what's the best practice? They've posed a multiple asset type across multiple market operators
Sure.
question, and sort of how do you approach that?
Okay.
And what's the best
So
way?
I'll take a shot at it, and if yeah, I'll feel free to repose it or email me. So in general, I mean, each market has quite specific constructs, and so adding assets in new markets requires a careful consideration of the particular opportunity in those markets. A 2-hour battery in ERCOT is worth a lot. Is worth a different amount than a 2-hour battery in CAISO, for example. And so I think the answer to how what is the custom is like carefully and with consideration, because of the sort of fragmented, federated nature of the U.S. power grid. I think there's a lot of value in doing kind of long-term forecasts and studies of potential value across the different markets. That just looking at kind of the long-term forecasts of power, ancillary service pricing, that can help drive that decision if one is looking to develop assets. On the other hand, in terms of acquisitions, if you have to look at what have been the hardware design decisions that have been made already, what kinds of constraints might be placed on somebody buying an asset that if it were sort of a greenfield asset might not have otherwise been there.
Yeah, I agree with all that Alan said, and if I could put a word on it, it's simulation. Is an extremely important capability that we spend a lot of time on, where if we're looking at adding a resource or moving a resource from a market, we're constantly simulating, okay, how much revenue would we get by enrolling this resource, or how much revenue would we get from hypothetically some other revenue stream if we remove the resource from the market. And STEM goes through this process fairly continuously, and especially with our aggregations of resources, we on a monthly basis will typically re-register the capacity and the specific resources which are enrolled in resource adequacy, because we have some customers who say the demand charge savings opportunity is greater for behind the meter resource, or for another reason, a battery needs to be taken out and essentially replaced by another one at another site to fulfill our contract commitment. So those STEM has a program operations team, which is day to day managing the logistics of enrolling systems and changing enrollments in these markets. And it's an ongoing process. But generally speaking, as Alan was saying, it does vary by market. The first step is to make sure that you are get into the model that the market operator uses to operate the market, and then once you're in that model, you can begin participating. But the lead time for that and the specifics of the process will vary.
All right, thanks. I've got a question that's directed to Dan. Question is, how do you balance between the ability to control the battery remotely with cybersecurity, and another question, between local and cloud EMS? How do you achieve that balance?
Yeah, great question. And this debate will probably go on for years. The way I would say that the right way is that you have a flexible EMS, an architecture that can shift. And in our case, we can make it to where the site controls, they operate autonomously, and there is no ability to receive cloud commands or receive AGC from anything other than the SCADA system. So, so for systems that are flexible, you could go from that architecture where it's all site controls, nothing from the outside other than the SCADA, all the way to a cloud system where you're waiting on a signal, on a power command from the cloud to come in, and that's how you're operating. So I would say it's going to be very important depending on the location on the grid, the size of your project, and also the size of the fleet that you own, how strict you have to be for cyber.
Okay, thanks. There's a few questions. I'm going to have to be selective here. Here's a quick one for Dan. Does Fractal Software also is Fractal Software also compatible with non-lithium ion technologies?
Yes. So we are operating EOS. We have lead acid. We have different types of lithium. Yes, and I'm hoping in the future it'll involve hydrogen and flow. So yeah, it's an overall architecture that will. I mean, you could operate a gas turbine or a solar plant if you want it configured that way.
Okay. So a question came in after the presenters, but it's not addressed to anyone in particular. So I'm gonna start with Dan, but then I think Josh and Alan might have an opinion on this. How do you manage operating modes for the battery at your EMS, not just for the market price, but also grid applications such as peak reducing, ancillary services, etc.? Do you have a control panel for all those modes?
Yeah, great question. And I didn't get to show it in the demo. There are quite a bit of things that weren't shown, but yes, we give you the ability, as you saw on the calendar, you can schedule stacks of applications, or stacks of modes, and so you have the ability to put in several things at once. You also have the ability to configure individual applications or individual modes with certain parameters, and you can have as many of them as you want, where maybe at 1 p.m. you have a particular voltage droop curve. At 2 p.m. you have a slightly different one. 3 p.m. Another slightly different one. So that is all possible, and pretty much any good EMS. I mean, Fluence is there. Pretty much everyone on the list is going to have capability of having different applications. Where there's a big difference from one EMS to the next is how difficult it is to create new applications. Sometimes it's a month-long process to change just one parameter in the configuration file, and sometimes it's easy. Now it's always difficult to create a new application because it might be something kind of special to the site, like a microgrid. Yeah, you want it to be easy to change the parameters within an application and make it slightly different.
Alan?
Sure. Oh, go ahead, Alan.
Okay. Yeah. So the way we treat these different products is that we, when the asset is, or when we, recommend a bid to be submitted to the market, we think about, the probability of being awarded for, energy or ancillary services. And obviously, if you're, awarded, for energy, the market operator will expect to dispatch you for energy or ancillary services. And so, we need to think about the state of charge for the asset. We need to think about point of interconnect constraints if it's a co-located asset. So there's a lot of, work that we do, in preparing the bid that, enables, ensures that the bid is, feasible, compliant with the market rules. But then, the dispatch of the asset itself is done on behalf of the market operator. That's not, we're focused more on the bidding part to make sure the bid, and then key to that is, that if bids are picked up, the asset can perform. But the SCADA and the actual telemetry of the dispatch instructions come from the market operator.
Yeah, absolutely. So, and that's the way we view different products, and essentially co-optimizing multiple revenue streams at a site is to consider the opportunity costs and the trade-offs of participating in one service versus another, and then also what are the other revenues that could be captured at the same time. So in the image I showed, there was a combination of solar charging, frequency regulation, real-time and day-ahead energy trading, participation in this various programs in Massachusetts in terms of Clean Peaks and Massachusetts Smart. And the way that we will build that optimization is to overlay those value streams next to each other, which tells us the best way to bid into the market, again, in accordance with the market's rules and other constraints on site, so that we clear and are dispatched in a way that maximizes the revenues of the system.
Yeah, this is Daniel again. Just one closing thought here. A good EMS is going to allow you to have both market applications and more local applications. So a combination would be, you're in an ISO, you're providing energy during a certain hour, but at the same time, you have a voltage droop curve that is specific to your location, and that's happening locally. So it's being able to have the combo.
Yeah, absolutely.
Okay. We're going to have to, boy, there's a ton of great questions here. Here's for Alan, how do you create the human trader benchmark? How is it defined and how is it created, and how do you get this data? And I just want to kind of broaden that, which is to ask, what are the ways that people quantify the advantages of AI or machine learning relative to human commands?
Sure. So, yeah, the manual trader benchmark I showed is just a simplistic representation of what a smart trader might be able to do. So, in our case, we take the basically buy low, sell high in the day-ahead market. We bid so some regulation chart, and bid every hour for spin. But we're not really considering kind of the stochastic range of prices. That really is where our optimization helps provides the advantage. I think in terms of metrics, I mean, the main one I showed was uplift, which is basically how much money in a given time period, typically a year, can you earn under different scenarios or under different kind of modes. We also have more specific metrics kind of for different components of our algorithm. But I'd say at the end of the day, I mean, we feel like the revenue versus what might be possible under kind of a simplified bidding out system that even a smart trader would employ is kind of the best overall metric.
Yeah, agreed. I think the human benchmark requires making some assumptions about the the logic that human would use, right? Like buy the 4 lowest and sell the 4 highest hours of any given day, and then when you bring in the artificial intelligence element, there's the perfect, what we would call a perfect foresight simulation, which is if we had a perfect forecast and we knew exactly what was going to happen with the market and with the other resources on site. Again, if we're co-located, what's the maximum value we could have gotten? And then there's alternatives that we could run to say, okay, what's the maximum we could have gotten if we limited the battery cycles to limited the battery to 10 cycles this month, or 20 cycles, or 30 cycles, or what's the maximum we could have gotten if we decided we didn't want to do frequency regulation because we're afraid of the wear and tear that puts on the system. So there's a bunch of counterfactuals that we can run. It goes back to that concept of simulation and being able to run those counterfactuals and figure out what the performance would have been to compare that to your actual and again to your perfect foresight.
Yeah, that's it's interesting. It'll be very interesting over the next few years to see how AI affects the economic evaluation of potential investments in terms of how close you will estimate how battery operation will get to perfect foresight. That concludes our presentation. We've arrived at the end of the hour, and I'd like to thank Alan, Dan, and Josh for a very informative session. We do have our annual conference the 1st through the 3rd of December in Phoenix. I'd like to remind you, take a look at our website for that information, and please stay safe and healthy, and have a great rest of the day. Thank you for attending.